Hello, my name is Chris Huang from OLEDON. It is an honor to be talking today. My presentation is about next generation plain source FMM evaporation for 10,000 PPI micro OLED. There are two types of micro OLED. The white micro OLED as a three-stack structure has around 25 numbers of thin film layer, providing high power consumption. Instead, the RGB micro OLED as a single stack structure has only 8 numbers of thin film layers, giving low power consumption. The CMOS substrate moves into the chamber to be aligned with fine metal mask. The organic molecules are evaporating to deposit on the metal plate as a donor film, which will be rotated to re-evaporate. The donor film molecules are vertically dissolving to provide patterned target film on a CMOS substrate to be out of the chamber. My rotatable plane source shows a rotatable flange connected to flat metal plate with wire heating and cooling assembly. Another photo shows a curved plane source for controlling of higher film uniformity and smaller shadow distances. The world's first plane source evaporator has been set up successfully for testing of shadow distance doping process and device processing in Dankook University. In order to see the possibility of 10,000 PPI micro OLED fabrication, the single pattern film was sliced in thickness profiles from the center of the pattern to the edge area of the pattern. The conventional source pattern seems to be all collapsed down as it goes lower. However, the plain source pattern is still alive even in the edge area of the pattern. It is showing 600 nanometer wide corresponding to 10,000 PPI. So the 10,000 PPI micro OLED can be fabricated using the curved plane source evaporation in the future. Huang's mixing re-evaporation process has been developed for doping process. The host CBP film and the dopant LP film are separately depositing on the metal plate to re-evaporate. During the re-evaporation process, the LP film molecules and CBP film molecules are diffusively mixing together at a single heating temperature to provide a homogeneously doped target film. A 6-layer green OLED device has been prepared to compare. The uniform dopant point source device has been made by conventional co-evaporation process, while the grading dopant plane source device has been made by the re-evaporation process to show higher emission and a longer lifetime. A metal plate moves in to be rotated during the point source evaporation. The uniform donor film will then be inverted for particle prevention process. The CMOS substrate moves in to be aligned with fine metal mask. Then the donor film will be re-evaporated to provide 10,000 PPI micro OLED device. A cluster-type plane source evaporator has been designed for pilot production of micro OLED. There is an RGB chamber, which plane source re-evaporation process, a donor film deposition chamber, an inversion chamber, a plasma treatment chamber, metal chamber, and a common layer deposition chamber. There is a PECVD and an inkjet printer chamber are connected as well for the thin film encapsulation process. A cluster-type plane source evaporator is designed for mass production of micro OLED. 3 cluster-type modules are prepared. The red, green, blue plane source re-evaporation chambers are distributed in first two cluster modules. In the third cluster module, two PECVD and two inkjet printers are connected for the thin film encapsulation process. To sum up my presentation, 1-gen point source, 2-gen linear source evaporation has been used for OLED production for many years. The maximum PPI number is still 600. The 3-gen plain source evaporator will produce micro OLED up to 10,000 PPI in the future in spite of multiple evaporation process. I believe it is time to challenge. This is my talk. Thank you for your attention. If you have any question, please send me an email. Bye now.